random circuit sampling. So yeah, take it away. And I guess just a reminder for the questions, if you could repeat the question, that would be great. Or and for the end, we'll pass the mic around. So great.
Sounds good. Thank you for the introduction and to the organizers for inviting me. I'm Shaun Datta. I'm a PhD student at Stanford. And today I'm going to share new work of mine on exponential improvements to the hardness of random circuits. This work will appear at Fox in December. This is joint work with my advisor, Adam Boland, Bill Pfefferman, and Felipe Hernandez. And I want to say at the beginning, interactive proof systems are very powerful, so I want to encourage you to ask lots of questions. So this is a talk about sampling from random circuits, for which there's a very beautiful theory that's flourished in the last 15 years. I want to share 3 perspectives on why this is so fascinating. So the first is that we've now seen many experiments that all solve variants of random circuit sampling. And it behooves us to ask, what is the power of these experiments? How compelling are they as potential violations of the extended Church-Turing thesis? And the second reason is more fundamental. Is quantum computing more powerful than classical? Is BQP different than BPP? This is the premise of our entire enterprise, that quantum computing goes beyond classical. And we have excellent oracular or black box evidence separating classical and quantum computation. What about white box evidence? Our dream theorem would be to separate BQP from BPP, but it's utterly beyond our current techniques to prove it. For now, it is only a dream. So what about the next best thing? Proving that BPP containing BQP would collapse the polynomial hierarchy, also well beyond our current technology. And the miracle is this. If we move from decision problems to sampling problems, we can actually prove this via sampling from random circuits. The first results are now 21 years old, so what's the problem? The problem is that these results are very brittle, in the sense that they're worst case and exact. They tolerate no imprecision or hardly any imprecision at all. For this to be more than just an artifact, we need to show that these results are robust, that they are robust to imprecision, and that they extend to the average case. And I'm here to tell you all these years later that this remains an unfulfilled dream. So in this talk, I'm going to try to convince you how much closer we now are to realizing this dream at last. So what's my take-home message for you? If you want to separate BQP from BPP for some computational problem, then this is your best bet. So our reasons to care so far are physics experiments and complexity theory. The third reason is cryptography. At the Simons Workshop, to kick off the reunion program, we heard about how so-called microcrypt primitives exist if sampling from random circuits is hard classically. So we'd like to remove the need to base these cryptographic primitives on unproven conjectures. That's why sampling from random circuits is worthwhile to study. Now let's all get on the same page as to what precisely these sampling problems are. They have 3 steps. First, you initialize some fiducial starting state. In the case of RCS, that's the all-zero string. Next, you evolve by a circuit drawn at random from some circuit family. So for RCS, that's a brickwork circuit with randomly chosen gates. For boson sampling, that's a randomly chosen linear optical circuit. And finally, you measure to generate a sample from the output distribution. So for RCS, that simply means measure in the computational basis. As an example, I've illustrated these 3 steps for boson sampling. And all we need to know about boson sampling for the purposes of this talk, is that its output probabilities are proportional to permanence of IID Gaussian matrices squared. So each matrix entry is drawn IID from the standard normal. Okay. Does anyone need a reminder as to what the permanent is? Okay, great. So remember, our motivating question is, how hard is it to simulate random circuits? I alluded to unproven conjectures, and now we'll see what those unproven conjectures are. Prior work showed that classical computers cannot sample from random circuits if it is sharply hard to estimate their output probabilities to within some additive error delta. Of course, that delta depends on which ensemble of random circuits you use, for random circuit sampling, delta goes like 2 to the minus n, the number of qubits. And for boson sampling, e to the minus n log n minus order log n, where n is the number of bosons. These quantities are essentially 1 over the Hilbert space dimension. And in the case of boson sampling, the conjecture that it is sharp p hard to this delta has a name. It's appropriately called the permanent of Gaussian's conjecture, recalling from the previous slide that the amplitudes are proportional to Gaussian permanence. And the central open problem is to prove one of these conjectures for any random sampling task. They are all open. Yes?
So if you have this conjecture, then you're saying it's hard to sample from random circuits, but up to what error? Is that also related to delta somehow? Or?
Yeah, good. So if you were to prove this statement, then this would say it's hard to sample even from a distribution that's close in, let's say, total variation distance.
Okay, like polynomially close or something.
That's right, yeah.
Cool.
Great. Any more questions? Okay, great. So what's the status of proving these conjectures? We want to show it's hard to estimate output probabilities to within plus minus delta, but so far we've only proven it's hard to within some delta prime that's much less than delta. This additive error delta is often called robustness, so this gap between delta prime and delta is appropriately called the robustness gap. And our goal should be to close the robustness gap. So what's the status? I've tabulated this for boson sampling, and there's an analogous story for random circuit sampling. So as we absorb this, let me highlight one thing in particular. Although the previous best robustness looks sort of close to the goal given to us by the permanent of Gaussian's conjecture, it's still exponentially far away in relative terms. So in this work, we improve the robustness so that it matches to the first 2 orders what's needed to prove PGC. So in the exponent, minus n log n, minus n, minus order n to the epsilon for any positive constant epsilon. But what's needed now to close the robustness gap is to improve this third term, 2 order log n. Are there any questions so far? I want to make sure that everyone's on the same page. Yeah?
Do you know off the top of your head what kind of scary function of epsilon it is in the epsilon that's being hidden by the big O?
Basically, like, what's the constant factor?
But it's like some function of epsilon, I assume. Like, there's some reason why you can't set epsilon to 0.
So this is for a constant. Epsilon has to be a constant.
Right. So is there some crazy functional dependence epsilon, like 2 to the 2 to the 1 over epsilon?
No. Actually, I think it's I think it's actually pretty tame, let's say. Great. More questions? Okay. So why has progress been so difficult? Well, there are classical algorithms that have solved related tasks, but maybe the deeper reason is that there are many known proof barriers, meaning that prior proof techniques could not possibly show hardness of sampling. Some are specific to boson sampling, some specific to RCS, some applicable to all species of sampling experiments. I'll highlight some of them in due time, but what I want to highlight for now is that in this work, we overcome all the known proof barriers. Okay. Our second major result is that we show that we can lift these new theorems to prove a hardness of average case sampling result. So our first major theorem is about the hardness of computing output probabilities, and our second result is about proving hardness of sampling. We prove that there is no classical sampler that fails for no more than 2 to the minus cube root of n fraction of instances of size n. Now let me say, despite seeming weak, all anyone knew how to prove before this was that there was no trivial sampler that succeeds on 1 minus 2 to the minus n fraction of instances. Of course, we want to show 1 over poly, so more remains to be done, but this is the first non-trivial hardness of average case sampling result. Well, okay, so first of all, this sort of looks like the trivial scaling, right? Meaning that essentially, if I were to guess an instance to within some precision, then you might imagine that if your scaling is so extreme, then you would just guess the correct answer.
So the RCS proofs were like hardness of worst case sampling or what?
Okay, so there has been work extending that to the average case. So for example, this work of Boland, Pfefferman, Nirke, and Bazarani. But the tolerance to imprecision was relatively small. Then there was follow-up work that made that larger, but still not quite what we need. Great, more questions?
On the previous slide, when you say you overcome all those barriers,
Yeah.
does it mean that you have a proof technique that is kind of depth dependent and kind of fails for
Exactly, yes, and I'll talk about exactly that thing shortly, but that's exactly right, yeah. Sorry, I realize I'm supposed to be repeating these questions. So the question was, if we're going to introduce techniques that will, in particular, for example, be sensitive to depth, and the answer is yes. Yeah.
I was about to ask a question, but your slide answers it.
Okay, great.
Sure. Just to make sure I understand, can you go to the next slide?
Yeah.
So this, what we want to show, this is implied by PGC, but you're saying that you have a separate proof that's getting you the like.
That's exactly right. Yeah. So okay. So let me repeat that. Right. So if we were to actually reach the goal, which is proving the permanent of Gaussian's conjecture, which is about computing output probabilities, then it would imply hardness of sampling. Right. Since we don't prove the PGC, it's not immediately obvious that there is an implication for hardness of sampling. So what the second result says is that, in fact, you can lift this result to prove a hardness of sampling result. It's just not as strong as the one we would like to show. Yeah.
So here by instance, you mean circuits?
So here, I mean, like you specify an n by n matrix to let's say log n bits of precision.
Right, but okay, so when you say there is no classical sampler that succeeds for an instance,
Yeah.
I'm thinking that you choose a random circuit and that is your set of instances, and then what does it mean to succeed for that particular circuit sample up to some constant TVD from the output distribution?
Yeah, that's right.
Okay, so but the closeness can be constant, you're saying, or inverse Pauli?
The total variation is its closeness. So here in particular, I'm talking about a multiplicative error sampler, right? So you imagine that you get each amplitude to within, let's say, like a 2 approx, something like that. Does that answer your question? Perfect. Okay, great. So
Sorry, but just
yeah.
So that's a little far then from like if you had the what's it PGC?
Yes, but to be clear, yeah. So if we were to enlarge our robustness to match that of the PGC, then it not only implies 1 minus 1 over Pauli sampler, multiplicative error sampler, it also implies this TVD, close in TVD sampler. Yeah.
Does the epsilon from earlier somehow go into this third root or?
No, actually. So the techniques that we use to prove this will be a little different, actually. Yeah, I think it'll become more clear once we see the proof sketch.
Wait, specifically cube root of n? It's not like any root?
Specifically cube root of n.
Okay, that's weird because the other result was any epsilon greater than 0.
That's right. Yeah. Good. Okay, so let's begin to sketch the proof. So let's begin with the standard worst to average case reduction, which harkens back to the proof of Lipton from 1991, which was then adapted by Aronson and Arkhipov. Now this is really a sublime proof from the book. So let's consider the permanent of R of t, a convex combination of a random matrix R, in this case IID Gaussian, and an arbitrary, say, binary matrix W. So this object has 3 desirable properties. Firstly, it's a polynomial in T of degree n. So this is just by direct inspection of the definition of the permanent. And by the way, here we're talking about the permanent, but for RCS, the degree is like the number of gates in the circuit. Secondly, the distribution of R of t is very close to that of R for small t. So this follows from a straightforward calculation. And thirdly, R of 1 is W. So this inspires the following reduction, whereby one uses the ability to compute the permanent of R to compute the permanent of W. So the key idea is polynomial extrapolation. We consider the permanent of R of t for small values of t, where by assumption we can compute its values, and we extrapolate a polynomial through those points to t equals 1, where we have permanent of W. Thus we can compute permanent of W if we can compute permanent of R. Hence, worst to average case reduction. The average case is as hard as the worst case. So what's the problem with this reduction? The problem is that polynomial extrapolation is terribly ill-conditioned in a sense that we can make quantitative using what's known as the Remez inequality. So it tells us that to estimate a degree d polynomial to within error delta on an interval, the blow up at t equals 1 goes like delta times the extrapolation distance to the power of the polynomial d. So from the Remez inequality, we get a very simple prescription. And the moral is this. To improve robustness, we need to decrease the extrapolation distance 1 over delta or decrease the polynomial degree d. Every technique we develop will have this purpose, to decrease one or both of these quantities.
Is this thing in both directions or only in upper bound?
Pardon me?
Is this thing in both directions or only in upper bound?
This is an upper bound. Yeah, but what we will show is that, in fact, the constructions that we have will saturate this bound. Does that answer your question? Great. Okay. So in our work, we introduce a suite of new tools to do exactly this, to decrease the extrapolation distance and decrease the polynomial degree. So coefficient extraction, dilution, the square trick, magnification, and 2 so-called rare events lemmas. So these tools get around all the proof barriers, and they exponentially improve our evidence for the average case hardness of random circuits, both for the robustness of estimating output probabilities and for sampling. So in this talk, I'm just going to focus on a few of them. Great. Our first idea to decrease the degree we call dilution. The basic idea is to shrink the worst case instance relative to the size of the random instance. So previous reductions used a worst case circuit, in particular a Fourier sampling circuit, acting on all n qubits. So here's a simple idea. Let's consider instead the circuit on the right, acting on n qubits with a bipartition into A and B. But now, only circuit WA is a worst case circuit, acting on n to the epsilon qubits, any constant epsilon greater than 0. And R of B is just a random but fixed circuit on the remaining qubits. So we've just shrunk our worst case circuit relative to n. And on the interface between A and B, we have identity gates. Is the picture clear so far? So the first immediate observation is that by construction, the output probability for this circuit factorizes. So for example, the probability to measure the L0 string is simply a product of the probability from WA and from R of B. And here's the key observation. Since WA is a worst case circuit, the probability to measure zeros on the A qubits is sharply hard to estimate multiplicatively. Okay? That's straightforward to see. You can work this out as an exercise. It's just padding. So this suggests the following strategy. Since I just argued that P0 of WA is sharply hard, what we now want to do is to show how we can estimate it given the ability to estimate P0 of a random circuit. That's what it would mean to give a worst to average case reduction. And since by construction the probabilities factorize, P0 of WA is P0 from the overall circuit divided by P0 of R of B. So what we need are multiplicative estimates to the numerator and to the denominator. The denominator we get for free. So since R of B is a random circuit, by assumption, we can estimate P0 of RB. Okay, what about the numerator? Well, Wn is a worst case circuit, so we can simply implement the previous worst average case reduction, but here we only extrapolate over the gates in WA. That is to say, all the circuits in our extrapolation path will share RB on the B qubits. So then the degree of the polynomial will shrink to the size of the support on WA, which is n to the epsilon. And remember, our error blowup goes like extrapolation distance to the polynomial degree, both of which we've decreased. So, after some arithmetic, we obtain robustness that is very nearly what we would need to reach the target of 2 to the minus n. So recall that for RCS, 2 to the minus n would suffice to show no classical sampling. Are there questions?
Is this the robustness you quoted earlier, or
Pardon me?
is this the robustness you quoted earlier as your result? Or?
So I quoted the result for boson sampling. This is the analogous result for random circuit sampling. And exactly what I'll do next is extend this technique, let's say, to boson sampling.
I'm still confused at the role RB is playing, because like in your reduction, you're not actually modifying the RB part at all, right?
That's right. That's right.
How? No, it's like feels like blowing yourself up by your bootstraps or something. Right?
Yeah. So remember, what we're given by the experiment is the random circuit, right? So we'll get R of A on top and R of B on bottom, and we'll have gates on the interface. That's handed to us by the experiment, right? So that's just what we get. But in a worst average case reduction, all you need to do is extract some sharp p-hard quantity given the ability to compute the average case quantity. Those are the rules of the game. And so in particular, you're free to shrink polynomially, let's say, shrink the size of your worst case instance.
So R of B is not actually a hard matrix, or how?
So
you can estimate it by assumption.
Yeah. I mean, so this is sort of like a proof by contradiction, right? You're saying, suppose that I have the ability to compute a random permanent. If using that ability, I'm able to compute a permanent that we know to be sharp p hard, then you've also shown that the ability to compute that permanent, computing the permanent of the random matrix is also sharp p hard.
And could you just say the argument for the robustness one more time? I think I just didn't parse it live.
Yeah, absolutely. So, yeah, I mean, this is sort of coming to us basically from this Ramez inequality that I shared, right? So what you get is your extrapolation distance, which we've decreased, to the power of the degree of the polynomial, which we've also decreased, right? So you're going to get something that looks like 1 over n to the epsilon to the power of n to the epsilon. And then that's what basically retrieves this sort of robustness.
It seems like you're trading off the classical hardness in order to do this thing, right? Like, because
how do you mean?
You are saying, okay, it's a polynomial time reduction, but still, right? To go from like this padding argument, you're failing a bit in this padding argument.
I'm not sure I quite understand what you mean, but
what's hard with respect to, I mean, okay, if we don't care about polynomials, yeah, it doesn't matter, but if we do care about how hard it is, and the classical hardness is actually now a bit
I agree.
less hard. Right?
That's right. Yeah. So it's only modulo polynomial time reductions. If you don't like that, if you like, if you have a different algorithm or whatever, then of course you're going to pay the piper for that.
okay, so now I'll come to Habinav's question. A feature of this argument is that it circumvents the depth barrier. So what is the depth barrier? We expect random circuit sampling to have a phase transition in depth from easy to hard. And intuitively, the reason is entanglement. a shallow circuit cannot entangle qubits as much as a deep circuit can. And indeed, there have been efficient classical algorithms, most notably from Knapp et al., that have been able to exploit this low entanglement using tensor network methods to sample from very shallow random circuits. Yet, prior hardness results were depth insensitive, whereas evidently, from these efficient classical algorithms, hardness of sampling can only kick in at sufficiently large depth. Now, our argument requires anti-concentration of random circuits. Why? Recall, we estimated a quantity that was a numerator over a denominator, and the denominator was the output probability of a random circuit. So this needs to be bounded away from 0, or the quotient blows up. And that's exactly what anti-concentration gives us, that this happens with sufficiently small probability. And the depth dependence is exactly what you would expect it to be, which is at log depth. Right? That's where the action happens for random circuits. Questions about this? Yeah, Jack. Oh, like 6, less than 6, if I recall correctly. So constant, a very small constant depth. Okay, great. So let's see, now I'll address maybe what Kunal asked. Let's see what happens when we try to implement this same strategy for the permanent. So remember, the idea of dilution is to shrink the worst case instance W prime to be polynomially smaller than the size n of the random instance. And again, by padding, the permanent of W prime is still sharp p hard. So our worst case instance W dilute looks like the matrix on the right. And so we'd like to implement the game plan that worked so well for random circuit sampling, which is to extrapolate 1 minus t r plus tw dilute to t equals 1. So when you try to do this, there's good news and bad news. Remember the moral. To increase robustness, we need to decrease polynomial degree or extrapolation distance. So the good news is that this does both. Okay, but now for the bad news. If W dilute has small support, as drawn here, then its permanent is simply 0. This follows immediately from the definition of the permanent. So polynomial extrapolation does not encode information about the sharp p hard quantity permanent of W prime. You just get an approximation to the number 0. So what are we going to do about this? Oh, let's consider instead R of t is R plus tw dilute. Let's simply drop the 1 minus t. Why would we do such a thing? The permanent at t equals 1 is just the permanent of R plus w. That's not very interesting. But the permanent of R of t does encode the sharp p hard permanent of W prime, and it does so not in its value at t equals 1, but rather in its leading order coefficient. So if you write out permanent of R of t in powers of t, you will see that it's a polynomial in t of degree n to the epsilon, and its leading coefficient is permanent of W prime times the permanent of the complementary minor R of d. So now what's the idea? We want to extract an estimate of permanent of W prime, but we only have access to it multiplied by permanent of Rd. But remember, by assumption, we have an average case algorithm to estimate random permanents. So now we can simply make a recursive call to that algorithm on a smaller instance Rd. So we can estimate the sharp p hard quantity of the leading order coefficient of perm of R of t, given the ability to estimate random permanents. Questions? Okay. A nice feature of our proof is that it circumvents the JSV barrier. So, okay, what is the JSV barrier? It refers to a celebrated paper from Jerem Sinclair and Vigoda 20 years ago that gave a polytime randomized classical algorithm to approximate the permanent of a non-negative matrix to small relative error. So if your objective is to approximate the permanent to within small relative error, the non-negative matrices are easy, and mixed sign matrices, meaning positive and negative entry, are hard. Yet prior proof techniques were insensitive to the difference between non-negative and mixed sign matrices. And by contrast, our proof is sensitive to mixed signs. Why is that? Well, our reduction obtains the worst case permanent to small relative error. So for this to be hard, the matrix needs to have both positive and negative entries. Questions? Abhinav.
In this sense, it's kind of similar to how you say that for RCS, it overcomes the depth barrier.
That's right. It's sort of analogous. Yeah. That's right.
I'm confused.
Kunal.
Like, so it's small relative error, but like, what did previous techniques do? That did they not estimate the small relative error?
They were deriving actually the exact
I see.
worst case permanent, right? Which is also sharply hard, even let's say for binary matrices. Great, good question. So now, I've sketched two of several techniques we developed to increase the robustness, to which we can show that it's hard to estimate output probabilities. And we can lift these techniques to prove a hardness of sampling theorem, but we need one last technique. So remember that the moral that framed all of our techniques is that to improve the robustness, we need to decrease the polynomial degree or decrease the extrapolation distance. And the suite of techniques we introduced to increase the robustness of estimating output probabilities gets us within striking distance of that goal. In particular, I claim that if we could estimate the permanent of R of t at t is 1 over root n rather than 1 over n, then we would show hardness of sampling. That won't be obvious, but I make the claim that that's what's needed after deploying our techniques. Okay, so what's the problem? The problem is that R of t for such large t is very far from IID Gaussian in total variation distance. So there's no guarantee that our average case algorithm will work so far out of distribution. But what we prove is that we can estimate permanent of R of t so far out of distribution if our average case algorithm works with sufficiently high probability. This is what allows us to prove a hardness of sampling theorem for a sampler that succeeds with this very high probability. So now we're going to set our sights exclusively on this goal of decreasing the extrapolation distance. Questions?
And just some understanding, did either of the things you show like decrease the polynomial degree at all?
Indeed, yeah. So for example, this dilution does.
Smaller circuit inside. That's...
Indeed, yeah, that's exactly right. This is like the last mile we need to go to get to what would suffice for hardness of sampling. Okay. And the key idea is this. Look at these two shifted Gaussians, which are distributions for a single matrix entry of R and R plus T shift W. The key observation is that R plus T shift W is also Gaussian, just with a shifted mean T shift. So in this figure, we have Gaussian G, shifted Gaussian G shift, and we color successful events blue and failure events orange. Our tail events in orange are that the algorithm fails. So remember our motivation. We want to estimate the permanent of R plus T shift W for a large T shift. And the figure illustrates that events deep in the tail of one Gaussian are still tail events for a shifted Gaussian with some much larger failure probability. So in particular, we prove that a tail event with probability e to the minus t squared under G has probability 1 over poly under G shift. That means that if our algorithm works with very high probability, then we can reliably estimate the permanent even for these far out of distribution values of t. Questions about this?
So, how does n here relate to the, I guess, dimension of the outputs for bosons?
Repeat that question?
How does n here relate to?
Oh, so to be clear, n here is the number of bosons.
Right, which is not log of dimension. Dimension is.
That's right. That's right. Yeah, these aren't qubits. That's right. Exactly.
So what would it be in terms of the dimension?
So I said, for example, that that the target for boson sampling looked like e to the minus n log n. Right? So this is like n to the minus n. But then there are two correction terms, which are minus n, so e to the minus n. And then you say this up to poly factor, so there's a minus order log n. Okay. There's another comment I should make here, which is that you can see we've tailored this argument to Gaussianity. Right? So in particular, whereas the first theorem that I shared with you applies just as well to random circuit sampling or to boson sampling, this is specific to boson sampling, as far as we know. Okay, so we show how to combine this with a very technical second rare events lemma that implies that there is no classical sampler that fails with probability 2 to the minus cube root of n for input size big N. So just as a reminder, that's of course weaker than what we'd like to prove, which is 1 over poly, yet it is also an exponential improvement over the trivial scaling. And until this work, all we could rule out was the trivial sampler. Now, I need to make a final caveat. Because we estimate R of t so far out of distribution, we need those far out permanents to anti-concentrate, just like we did in our dilution proof. That doesn't immediately follow from standard permanent anti-concentration. But in the paper, we show that in some sense, it interpolates between standard permanent anti-concentration, which holds at t equals 0, and for large t, where it's actually proved outright. So we merely conjecture that it's true in between these two extremes. So if you're an anti-concentration buff, I would encourage you to take a look at the technical details in the paper. Happy to discuss more. Yeah, Kabir.
What is capital N here again? It's not the number of photons.
That's right. So this is you have to quantify in terms of sort of the native input size to the problem. And the native input size to the problem is not little n.
Okay.
Right? It's not the number of bosons. To specify the input to the problem, you need to give an n by n, little n matrix with each entry specified to, let's say, n log n bits of precision, right? So you're actually going to have some order tilde n cubed, little n cubed size input. So that's basically what this big N looks like.
So where did the cubed come from again? You said there's an n by n matrix.
And you also have to specify each of these to some number of bits of precision.
Okay. Great.
Great. Yeah, Kunal.
How significant is the cube root? Is this where the cube root is coming from?
Exactly. Yeah. So this is exactly where the cube root comes from, right? Precisely that. Quantifying it in terms of little n, let's say this is like 1 to the e to the minus order n, but that's actually very misleading, because that would lead you to believe that sort of that looks like the trivial scaling, but actually the input size is order n, little n cubed, up to log factors. Yeah.
Sorry, why is the input size n cubed, not n squared?
I mean, you also need to specify sort of each of these entries, right?
Oh, each one's a polynomial.
Indeed, yeah.
Got it. Good.
Great. Good question. Okay, great. So other than proving that generalized anti-concentration conjecture, I have just one open problem to pose to you. With no more proof barriers in the way, can we at last prove the permanent of Gaussian's conjecture? That is the open problem that I set to you. So with that, I thank you for listening, and I'll invite you to ask more questions.
Okay, so thanks, Shaun, for a great talk. We have a lot of time for questions, actually. So, any questions?
The obvious question: what's your answer to your last question?
To this question?
Yes. Do you think?
Well, I'm hoping you'll help me. So I've thought a lot about this problem. My advisor also tricked me by not telling me that this was an open problem for more than 10 years when he gave it to me. So that's a good way to get your student to solve something they would otherwise be intimidated to work on. I think what's really exciting about this, and this is not like a throwaway open question. I actually think that with these new techniques, we're maybe one or two good ideas away from actually solving the problem.
Okay, maybe I can specify the question. Do you think these polynomial interpolation techniques will be enough? It seems like you've sort of squeezed everything out of them now. Like you've made everything sort of polynomially tiny, and yeah.
Yeah. So the question is, will these polynomial extrapolation techniques be enough? It sort of seems like you squeezed all of the juice out of them. And that, I mean, certainly if I had an immediate idea where I knew how to improve things, I would improve them. So in some sense, that is sort of true by construction. But I will say before we started this project, that also seemed to be the case, right? So in particular, like these barrier results, I think can mislead one into thinking that sort of there's no way around them. And often it just takes a little bit of human ingenuity. Yeah, but that's a great question. Yeah.
So if I remember correctly, any proof of the permanent Gaussian conjecture, I think, needs to be non-relativizing, right? Is this also not this proof of?
Yeah. So that's a great question. So the question was about relativizing and non-relativizing techniques. So here, for example, the sampling theorem that we show is a multiplicative error sampler. Right? So for example, there's work of like Aronson and Chen that showed that there's like a relativization barrier for TBD approximate sampling. But it is also true that if you would prove the permanent of Gaussian's conjecture outright, then that does also imply this close-in TBD sampler.
Right.
And that's why that's our target. Good, very good question. Yeah, Scott.
So given these, wonderful results and everything else, like and everything else that we know now, like how does the situation for boson sampling compare to the situation for random circuit sampling?
That's also a really good question. Okay, great. So the question is how do the pictures for random circuit sampling and boson sampling differ? So, okay. If we look at, for example, the hardness of computing output probabilities, right, this first theorem, because there's not an analog of the second theorem to random circuit sampling, it looks like the boson sampling result is closer, right, in the sense that, we have this, should I jump all the way back? Let's see. So, right. So, we can see that, in some sense we're sort of only off by a constant factor in the exponent, right? So that looks very close. On the other hand, right, in these results, we assumed anti-concentration.
Right.
Whereas for random circuits, anti-concentration is a theorem.
Right.
So
right.
I would say they're just different.
Right. Right. Well, I would say one salient difference for me is just that the boson sampling distribution really does look more heavy-tailed.
Yeah.
Right, like
Yeah, yeah, yeah.
anti-concentration seems like.
That's right. That's right. Yeah. I will say, yeah, if I had to pursue only one of them in an attempt to prove the sort of hardness of computing targets, then I would pursue boson sampling. But that's large error bars on that statement.
Yes. Plus or minus 1 over Pauli.
Yeah, exactly right.
Other questions? Maybe I have a question actually, which is suppose we just know that PGC is true.
Mm-hmm.
Can you say a little bit like what our picture of the world would be like at this point? Like you mentioned, like connections to sort of complexity theory at the beginning. There's also questions of like, what does this mean for like, should we use random circuit sampling or boson sampling as tests of quantum advantage?
Yeah. Okay, that's a really good question. So just to restate it, the question is sort of, let's say PGC is true. So what? What does that tell us about the world? Like, what new would we learn? And you know, for that, actually, I want to go back to this motivation slide. Yeah, perfect. So, you know, I would sort of give the answer in 3 parts based on the 3 motivations. So, of course, the first is that people are really doing variants of random circuit sampling in experiments. And as scientists, it's a good idea to ask sort of what is the theory that underpins these experiments? And okay, that provides some more sort of compelling evidence. But I wouldn't say that's the main reason, actually, because there are lots of other wrinkles in that picture that I don't want to get into, but I'd happy to discuss offline. Really, to me, there's this huge complexity theory motivation, which says that there is actually some well-defined computational problem. It's a sampling problem, for which there is a distinction between classical and quantum computation. I mean, I think that's a really beautiful thing. And then, you know, this really amazing new motivation for us coming from cryptography, you know, if just to sort of paraphrase the Karano-Tomer result, their second from 2024, you know, you get all of this rich cryptographic landscape in microcrypt. So you get quantum bit commitments and secure computation and so on, one-way puzzles, under very mild complexity theoretic assumptions, sort of morally like p to the sharp p is not contained in BQP, which is very mild, if the permanent of Gaussian's conjecture is true, right? So that would really mean that we get this sort of rich cryptographic landscape under very mild complexity theory without other unproved assumptions. But to me, that's a very compelling motivation. Yeah, great question.
Thanks, that's super nice. I actually have one more question.
Yeah.
Hope this is not getting to a wrinkle you didn't want to address, but do you think these ideas on interpolation might also yield some insights into verifying random circuit sampling?
I hope so. I mean, I think that is sort of the glaring open problem, right, for quantum advantage schemes. So I think, well, I don't have a good answer to that question, but I think it's a good question.
Anyone else? If not, maybe we'll thank Shaun again and take a slightly longer break. So we will be back at 3:30 for the next talk, I believe. So see you guys then.
Very nice.